Hi everyone. Today I want to talk about Levity polymorphism. So I've been trying to talk about Levity polymorphism for the last few weeks, but it takes quite a bit of background to get there. So in contrast to what I like to do in my videos, I actually think that this video is really going to build on what we did last week. I'll have a very brief review at the beginning, but you may want to watch last week's video on how we use capital type to track representations in kinds, and then this video will make a lot more sense. I'm sorry for that, but sometimes we just have to build on prior knowledge. So this example that I'm working with here is all about defining this parity integer type, which is just, it's storing an integer along with its parity, whether it's even or odd, because suppose it's hard to calculate that. So we want to store it alongside the integer, as well as have numerical operations on it. The problem is, our starting problem is that this muck-pi, well, what it means is that when I make this pair of parity and integer, this muck-pi constructor allocates a little bit of extra memory that just stores all of these pointers. And I want to get rid of that extra memory. So I use parity integer hash. Now the hash mark is just the naming convention. It doesn't really mean anything by itself, but this is the magic hash extension, which allows me to put this hash mark here and is useful for readers of the code to know that something weird is going on. Here, I'm going to store this using a new type, and it's a new type wrapping around the unboxed pair parity integer. So what this means is that an unboxed pair is just two things that are passed around with each other. There's no extra memory that's taken up with them. So when I call a function and pass in an unboxed pair, it's just passing two arguments. When I have a function that returns an unboxed pair, it's just returning two things in two separate registers on the machine. It doesn't allocate any extra memory. It's very nice and fast. So here, when I say that parity integer hash is really just a new type around an unboxed pair, it doesn't have the same representation as all of these other things, right? My parity integer type up here is represented by a pointer to this little structure that has two more pointers. Down here, my parity integer hash is not represented by a pointer. It's really represented by this pair of two pointers that doesn't allocate any extra memory. And so when I do that, that changes the kind of parity integer hash. That's the subject of last week's video, also linked from the description, by the way. And here, I'm saying that this representation, that's what this type says. This type is describing the kind of some type, and then I say what the representation is. So here it's tuple rep, meaning it's one of these unboxed tuple things, and the two pieces are both lifted rep, and that's because both parity and integer are actually, those are represented by pointers. So lifted rep is sort of our basic normal representation. I should say that in newer GHCs, I can't quite remember which release it's in, is it 9.0 or 9.2, lifted rep is actually a synonym for boxed rep lifted. I'm not going to demonstrate that in GHCI because I don't have that in the GHC that's running right now, which is 8.10. But we can imagine, right, lifted rep says, or rather boxed rep is that it's represented by a pointer, and is it lifted, in other words, lazy, or is it unlifted or strict? And so we can sort of keep track of these things separately. Okay, so that's the very brief introduction, just to show a little bit more of what's going on. I can ask here, what is the kind of int hash? So int hash is the built-in type of actual machine ints. So here its representation is int rep, because this is not represented by a pointer. It's just represented by a machine integer, and that's what int rep really means. If I look at the kind of the unboxed pair constructor, we get this. No, we don't. That doesn't look right. Let's set f print explicit runtime reps and try that again. There we go. That's what I wanted. So just briefly, what this does is that these type blah things that we're looking at, well, they can be quite scary to the uninitiated. And so GHC by default tries to smooth this out and hide some of these details from you. I think in the type of the unboxed pair constructor, that's not very helpful, but in other things, it is. A key example is in the type of dollar. Oh, it doesn't show up there. Let's try type plus v of dollar. There we go. So this plus v means GHC, don't mess with it. Just give me the real type. Newer GHCs do this by default, but 8.10 didn't. And so here, dollars is something that you might learn on, day 2 or day 3 of Haskell. And we really don't want people to see this very complicated type. So this fprint explicit runtime reps shows us the type that we see here. If you don't specify that, then you get a much simpler type, which is friendlier on day 2 or 3 of Haskell. Okay, going back to this, right, we see that the unboxed pair, well, it takes something that's type K0, so it has some representation, we don't know what, something else of some other representation K1, and the representation here is just a tuple of K0 and K1. And that's because these unboxed tuples don't really exist at runtime. It's just sort of a grouping construct. What I want to talk about today, so this is all about how we represent representations, but what I want to talk about today is how we can make this parity integer hash more convenient to work with. So here, I was able to write a function that returns a parity integer hash, and I was able to add 2 parity integer hashes. But then this big PI hash, I had to use a rather unusual way of describing a sum of all of the numbers between 1 and 100,000, right? I would much rather just call the sum function than do this, but I can't do that. And that's because the sum function expects to work with lifted types. And here I have an unlifted one, this parity integer hash. So let's explore a few fun things we can do, and this will bring us to Levity polymorphism. So the first thing I want to do is this integer from PI, oh no, not this one, this PI from integer hash. Really, that should just be from integer. Of course, I can't use the real from integer. If we look at the type of from integer, let's do t plus v of from integer. So from integer is the method in the num type class that GHC uses to implement overloaded numbers. And so here, whenever in a program I say just the number 3, really it's a call of from integer 3. And so this allows me to have 3 have type int sometimes, and 3 can also have type double. That's because both int and double have num instances. What I can't do is 3 of type int hash, I get problems, or 3 of type parity integer hash. And the reason, it's not because we're missing a num instance. The first problem is couldn't match a lifted type with an unlifted type. And that's because if I look at the type of from integer, I get this, let's set print explicit for alls. And if I do this again, then we see it's for all a, as long as a has a num instance, then it changes an integer into an a. What's unwritten here, and I don't think there's a flag that will get GHC to print it, but what's unwritten here is that a has type, has kind type. So a really has this kind here, it's type, which is the same thing as type of lifted rep. And because of this, when I try to instantiate a to parity integer hash, I get an error like this, that a has kind star, that's just the GHC way of printing out type, whereas parity integer hash has this other much more glorious kind. So this num isn't going to work. Instead, I want LP_num. So LP_num is the Levity polymorphic num class, and here A is going to have type R for any representation R. And so I'm going to need 2 functions here. We're going to do LP plus, which takes an A to an A to an A, and we're going to have LP from integer, which takes an integer to an A. So far, so good. This is just leftover GHCI gunk. Okay, so this is good. I can have an instance of LP_num for regular old integer. So here LP plus is just going to be plus, and LP from integer is, I hope, just from integer. Does this work? Yes, it does. But I can also write an instance LP_num of parity integer hash, where in this case LP plus is going to be, what is it called? I think it's add hash. Yes, add hash. And LP from integer is PI from integer hash. Whoops. Aha. So now, using this LP_num, I can actually use, instead of just integer, instead of PI from integer hash, I can change this to LP from integer. Does that still work? It does. And so I've taken one step closer to making big PI hash. Wouldn't it be nice if the exact same code could be written for big PI hash as it could be for big PI? So already I've written LP from integer. Let's see, instead of having add hash here, I can have LP plus, hopefully. Yes, I can. And now, well, there's this PI from integer. So really now what I need is I need two integer. So I can write that LP to integer. So A to integer here. And then now I need this. So LP to integer, well, this is just going to be id. And LP to integer is integer from PI hash. Is that good? Oh, wow, it is. Okay, so now that I have this, instead of, what am I trying to do here? So instead of PI from integer hash, this is now LP from integer, I think. Yes. Is that everything? I think that is. So if I change this hash mark and I just get rid of it, and then let's just comment out this type signature. It turns out that we won't need it. Does that still work? Oh, now this is no good because I'm using this integer from PI hash. I don't want to use that anymore. Let me use LP from integer. Sorry, LP to integer, I mean. And then now what's gone wrong? Something has gone wrong. No instance for LP num parity integer. Well, that's because I have a num class, but not an LP num. So I can fix that. That's easy. I can say instance LP num parity integer, where very boringly, this is going to be just the same because I do have a good num instance. Oh, but this last one, LP2 integer, muckpi blank I equals I. Okay, let's see. Now what's going wrong? No instance for num parity integer arising from the use of plus. Do I really? Wait, I thought I did have a num parity integer. Do I not? Oh, I have num parity. Haha, that's very silly of me. Instead of plus, I think I just want add. And instead of from integer, I think I want LP from integer here. Oh, wait, no, not LP from integer. PI from integer. Does that work now? Oh, now there's still something wrong. Couldn't match this with that. Oh, I did it in the wrong spot. That was very silly. You probably saw that, didn't you? I want this like this and this like this, please. Yes, haha. Okay, so what's the upshot here? So the upshot here is that now my definition, big PI hash, is really using the overloaded capability and sort of this ad hoc polymorphism, this class-based polymorphism in Haskell. And that all I have to do to change my program is change the type signature. So here I have big PI hash. It still has the hash in the name, but again, that's just the naming convention. It has type parity integer, and it works. If I just add the hash mark here, oh, blarg. Now what's going wrong? Couldn't match a lifted type with an unlifted type. Aha. That is very interesting. So let me first prove to you that if I just uncomment this type signature, it works. Okay, so it does work. But then why did I get that error before? If I comment this out, now what that means is that at this point, GHC has to infer a type for Go. There's nothing in Go that tells me what the type of this ACK argument is or the result. We can figure out through type inference that the type of ACK and the result has to be the same type, right? Actually, we can see this quite easily in this first equation. But all that we can deduce from these two lines of Go is that whatever this type is, it has to have an instance of the LP num type class. So you might hope that we could infer maybe a type that looks like this. And on the surface, that actually looks like a good idea. In fact, I think this might almost type check. I don't expect it to really type check. Not in scope, type variable R. Well, don't do that. Let's give it. It's a runtime rep. Now what do we get? Aha, a Levity polymorphic type is not allowed here. So let me explain a little bit about what's going on. I claim, knowing the internals of GHC as I do, I claim that this error means that this actually did type check. That this is a correct type to describe this implementation. However, we have a really big problem. We can't compile Go. And that's because I don't know what the representation of A is. It is representation polymorphic. It also happens to be Levity polymorphic, and we use that term a lot. But really, the interesting part is that it's representation polymorphic. When I'm compiling a function like Go, I need to know how to actually make instructions that will run on my machine to perform the actions in the Go function. In this first case, what this action is it has to take this accumulator and return it. On an architecture where the first parameter to a function is in a different register than the return value of a function, then that means I have to move this argument from whatever register it's passed in into some other register where it's returned. But I don't know the representation. And that means I don't know how big of the register it is. Maybe this is going to be a machine float. Maybe it's a machine double. Maybe it's a machine byte. Maybe it's a pointer. We don't know. That's because here I said that A has kind type R, and we don't know what R is. So even though this type for Go makes perfect sense, and even if we follow through type checking using all of the rules that we can write down in typing rules, works here, the back end of the compiler, the part that actually asks to produce instructions, is completely at a loss. We don't know how to compile this function. And so because of that, beyond just the normal type system rules, we have constraints around Levity polymorphism. The particular constraint that's in play here is that we cannot ever, ever, ever bind a variable whose type is Levity polymorphic. Or rather, let me try to spell that out even a little bit more clearly. We can't bind a variable whose type has a kind that has a variable after the big capital type. And so we can't ever have a variable ACK of type A. And so and when you try to do that, you get a Levity polymorphic type is not allowed here. And this means that you've violated this restriction. So I'm going to comment out this sort of very general type for Go, which I would love to be able to compile, except I really don't know how to. And instead have this much more restrictive type for Go, which now fixes the representation. So this works. There's actually a middle ground in that, let me comment this one out. And now, instead of saying for all runtime rep, I could have this work for all types that are represented by two lifted pointers next to each other in memory. So here I've specified the representation for A. I have not said anything about parity integer hash. Does this still work? I hope so. Oh, it doesn't. Why doesn't it work? Parse error. Well, that's a simple-ish problem. Yes, I need an extra close paren. Now does it work? Yes, it does. And that's because I've now given enough information to the compiler to know that when I copy ACK from an argument to a result, I actually have to copy two pointers from two registers into two result registers, right? That information is buried here. And so it's enough information so that the compiler can proceed. It doesn't need to know that this actually is a parity integer hash. I might have other types with a representation of two pointers that are squished next to each other. There could be many such types. And this Go, as long as there's an LP num instance, will work for any of them. So you might also wonder at this point, how can I write all of this? So here, LP plus, if we look at A here, A has this kind type R. And it looks like I have arguments of type A, so this is bad. But I very cleverly never bind a variable with type A. All of these definitions are, we call it eta reduced, means I haven't written the arguments out. But actually, even the fact that they're eta reduced isn't all that important, because in all of these cases, I'm at a particular instance. So at this point, R is known. Here in an integer, it's lifted rep, right? Integers are represented by pointers. Parity integer is also represented by a pointer, so my R is also going to be lifted rep. Here in a parity integer hash, it's not lifted rep, it's this tuple rep, lifted rep thing that we've seen a bunch of. But it still means that it's fixed. And so if I were to say something like xy here and xy here, we're still okay because at this point I know what r is. This is not a variable whose type has a kind with an unknown representation. I very much know the representation at this point. So what we see here is that by using a class like LPNum, we can sort of sidestep this Levity polymorphism restriction and have a type that's general enough, or have a class that's general enough to work with both lifted types and unlifted types. For the num class, there isn't really a catch here. So one possible future includes taking our near and dear num class as it's baked into Haskell and actually generalizing it to be much more like LPNum. Maybe there are some downsides and we might get some worse error messages. So I don't accept that. That means we have work to do to try to not get worse error messages. But the naive first attempt might do that. And so we would have to fix that problem. We would also make things potentially more confusing for newcomers, because if they look at the definition of num, now there's all of this extra fanciness. And so how do we deal with that? It's a really good question. I don't know the answer to that question. It's something that we struggle with, is that Haskell is such a flexible, powerful language that we can have these really powerful things like LPNum. But yet it's so powerful that and we can actually hide most of that from the users in day-to-day work. But then if they examine the code or use :info or something, they see all sorts of stuff that they don't know about, and that's not really a very good experience. I don't yet know how to mediate between the needs of experts and the needs of new learners. But I know that figuring that out is important. So this has been this small introduction to Levity polymorphism. We've seen a case here where we both see a Levity polymorphism restriction in action, but yet we can get around it using classes, which is sort of a clever trick. We didn't really know that was going to happen when we started to write the Levity polymorphism paper. And it means that we can have code that's really quite generic over both lifted types and unlifted types, and just through a few type signatures drastically change our program's strictness and how it runs. I hope this has been interesting. Thanks very much for watching. Bye.